Imagine for a moment that it is late at night. The air is quiet. The day's noise has settled into memory, and you step outside beneath a wide and waiting sky. The world around you rests in shadow, but above, the heavens awaken in their endless brilliance. Stars gather like scattered jewels across a black canvas, and in their silent glow, you feel something both familiar and unknowable. It is here, in the company of these distant lights, that we begin our journey into the size of the universe. Take a breath and let your eyes wander upward. Perhaps you see only a handful of stars at first, the brightest ones, those that have always guided sailors, poets, and dreamers. But as your gaze softens, as your vision adjusts, more and more appear. 1,000 pinpricks of light, and then more than 1,000, until the sheer number becomes difficult to hold in your mind. What looks like a simple sprinkle of light is already more than you could count in a single night. And yet, what you see is only the tiniest fraction of what exists. For every star you glimpse with the naked eye, there are countless others hidden by distance, by faintness, by the veil of time itself. The universe does not reveal itself all at once. It asks us to look carefully, to listen patiently, to wonder with humility. As you stand beneath the stars, you are standing in the middle of a story billions of years in the making. Those points of light are not scattered randomly, but each one has its own history, its own birthplace, its own arc through time. Some are young and burn with fierce blue heat. Others are ancient and fading, their light softening into amber. Some stars shine alone, while others are bound in pairs or even families, orbiting each other in silent cosmic dance. Each one, near or far, contributes to the immense tapestry that stretches across the heavens. Now imagine lifting your gaze higher still, beyond the stars visible to you. Beyond them lies the pale river of the Milky Way. It may look like a faint band of mist, stretched across the sky from horizon to horizon. But that mist is not made of vapor. It is made of stars, billions upon billions of them. Packed so closely together from our perspective, they blur into a continuous glow, like grains of sand forming a shining shore. To see the Milky Way is to see your galaxy from within, to look sideways across the grand spiral arm in which you live. Pause here. Feel the weight of that thought. You are not simply a person on the surface of a planet. You are a citizen of a galaxy, carried along through its rotation, part of its endless unfolding story. The galaxy does not announce itself loudly. It reveals itself softly, like a whisper across the night, reminding you that even in stillness, you are moving, circling the center of the Milky Way at unimaginable speed. It is easy to feel small beneath such immensity, but perhaps small is not the right word. Perhaps connected is better. For every atom in your body was once forged in the heart of a star. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was created in furnaces of light that lived and died long before Earth was born. To stand beneath the stars is to recognize kinship, not distance. You are not beneath them, not apart from them. You are of them. Think of light itself. Each beam from a star is a traveler. Some of those travelers have only just begun their journey, shining from nearby suns, only a few years away. Others have crossed thousands of light years, moving steadily across the dark, year after year, century after century, before finding their way to your eyes tonight. When you look at the stars, you are not looking at the present, but at memory. Every star is a story from another time, and together they form a vast library written in light. Close your eyes now and imagine peeling back the layers of distance. First, the nearby planets that share your sun. Mars glowing red, Jupiter with its swirling storms, Saturn crowned with rings. Beyond them, the nearest stars flicker, small but steady. Then farther, clusters of stars gather in constellations, like ancient campfires burning across the night. Behind them, the Milky Way stretches wider, filling your vision with its boundless reach. And still beyond, more galaxies spin, silent pinwheels of light, so distant that their shapes blur into tiny smudges. Layer after layer, the universe expands before you, each step larger than the last, until the scale becomes almost impossible to grasp. And yet, even as the mind struggles to imagine such distances, the heart can feel their wonder. There is no rush to measure, no need to calculate. You need only drift, as though on a gentle current, letting the vastness unfold in its own time. The universe is not asking you to conquer it. It is inviting you to notice it, to rest within its immensity, to feel the peace of belonging to something so beautifully endless. Look again at the stars above you. Somewhere among them, planets circle unseen. Some are barren, some icy, some perhaps warm and welcoming. Around distant suns, there may be skies with colors you cannot imagine, oceans deeper than any on Earth, mountains higher than Everest, winds that sing across alien plains. The universe is not only big in distance, it is big in possibility, in the endless variations of worlds that could exist. Every star you see could be a sun to another sky, another story waiting to unfold. This is where our journey begins, not in measurements, not in numbers, but in awe. To ask how big is our universe is not only to seek a figure or a boundary, it is to ask how far our wonder can reach, how wide our imagination can stretch. Tonight, standing beneath the stars, you begin to feel the answer not in your mind but in your spirit. The universe is not only around you, it is within you, a mirror of the stardust that forms your body and the curiosity that moves your thoughts. And so, as the night deepens and the stars grow sharper, let your heart quieten. Let the immensity of the sky cradle you. You are walking beneath the stars, but you are also walking within them, carried by their light, held by their vastness. The universe is already opening itself to you. This is only the first step. Step gently away from the faint shimmer of distant stars and bring your attention closer to the neighborhood you call home. Not the streets of your town, not the hills or forests, but the cosmic neighborhood, the sun and its companions, the planets that dance around it, and the nearby stars that share its corner of the galaxy. To understand the size of the universe, we first begin here, in the quiet company of our solar neighbors. The sun is the anchor of this neighborhood, a constant presence in the sky, though often taken for granted. Its light reaches us in just over 8 minutes, a cosmic heartbeat that reminds us that even the closest star is far beyond our ordinary experience. Yet it is our nearest star, a glowing ball of hydrogen and helium, holding the planets in orbit with an invisible hand, shaping life on Earth in ways that are both subtle and profound. Look at Mercury, closest to the sun. It is small and barren, a world of extremes, its surface scorched in the daytime and freezing at night. Venus comes next, shrouded in clouds that trap heat like a furnace, hiding a landscape both mysterious and hostile. Then Earth, spinning serenely in its perfect orbit, a blue and green gem in a vast darkness. Mars, red and rugged, waits silently, its deserts and canyons whispering stories of a distant past when water may have flowed freely. Beyond Mars lies the realm of giants. Jupiter, a massive sphere of swirling storms, each one larger than Earth, radiates energy as if the heat of its formation never quite left. Saturn follows, majestic with its rings, a halo of ice and rock that catches the sun's light in a dazzling display. Uranus and Neptune, distant and cold, drift in quiet blue solitude, icy giants at the edges of our system, reminders of the vastness even within our own solar neighborhood. And beyond the planets, there are countless smaller bodies, asteroids, comets, icy objects at the fringes of the system, each moving along its path, each a silent witness to the history of the sun. Some may collide, some may wander close, and some may travel into interstellar space, leaving our neighborhood forever, carrying fragments of our solar story into the galaxy. Now consider the distances. Light from the Sun takes just over 8 minutes to reach Earth. Mercury is slightly less, Venus slightly more, but Jupiter about 43 minutes. Neptune over 4 hours. Even within the confines of our system, the distances are enormous compared to anything we experience on Earth. Each planet, each moon, each comet moves through space that seems almost impossibly vast, even though all of it is bound together in the Sun's embrace. Beyond our own system, the solar neighborhood extends to the stars nearest to us. Alpha Centauri, a trio of stars, including the bright Proxima Centauri, lies more than 4 light-years away. That is about 25 trillion miles, or 40 trillion kilometers. It is a distance so large that even traveling at the speed of the fastest spacecraft ever built, it would take tens of thousands of years to reach. And yet, in the cosmic scale, these stars are our neighbors, close enough to exchange light, close enough that their gravity gently tugs on ours, shaping our place in the Milky Way. Other nearby stars include Barnard's Star, Sirius, and Wolf 359. Each has its own planets, its own mysteries, perhaps even worlds with climates, oceans, or deserts unlike anything on Earth. Some may harbor nothing at all, vast barren spheres orbiting cold, dim suns. But the possibility of life, any form of awareness that gazes upward from those worlds, connects us in imagination to places far beyond our reach. Now let your mind wander further to the larger pattern. Our solar system is not alone in the galaxy. It is part of a vast collection of stars that move together in what astronomers call the local bubble, a region of space in the Milky Way where stars, gas, and dust form a neighborhood of hundreds of light-years across. Our Sun moves through this neighborhood at an astonishing speed of over 450,000 miles per hour, orbiting the center of the galaxy once every 225 million years. It is a silent, unstoppable journey, almost too slow to notice on a human timescale, yet breathtaking when seen across the expanse of time. Imagine the cometary clouds at the edge of the solar system, the Oort cloud stretching halfway to the nearest stars, a frozen boundary between the Sun's influence and interstellar space. Each icy body drifts slowly, orbiting a distant center, a frozen reminder of the system's origins. Occasionally, one of these objects is nudged by a passing star or gravitational ripple, sent plunging inward to become a comet visible from Earth. A fleeting visitor that reminds us of the vast, dynamic cosmos surrounding us. And yet, even these distances, even these countless bodies, are mere whispers compared to the galaxy as a whole. The Sun, planets, and nearby stars form but a tiny patch in the Milky Way, a spiral galaxy home to hundreds of billions of stars, each with its own planets, moons, and possibilities. But for now, in our quiet meditation, we linger in the solar neighborhood, letting the enormity of it sink in. Consider the scale of this neighborhood. The nearest star, 4 light-years away. The Oort cloud stretching halfway to that distance. The planets circling in their silent orbits. The Sun's light traveling across millions of miles to reach your eyes. And beyond this, the Milky Way beckons, full of stars, clouds of gas, and untold mysteries, stretching across 100,000 light-years. But we are not yet ready for that grand view. Tonight our journey remains intimate, focused on the region that cradles our own existence. Pause and breathe. Imagine gliding past Neptune, past the scattered icy objects, beyond Alpha Centauri, watching starlight streaming past you. Even here in the calm quiet of our neighborhood, there is a sense of motion, of infinite subtle change. The solar neighborhood is not static. Stars are born and die. Comets and asteroids wander through space. Planets shift slightly over eons. Gravity pulls and tugs, shaping paths that are both predictable and astonishingly complex. Notice how the distances make your mind stretch. Even at the speed of light, a trip to the nearest star would take over 4 years. To cross the Milky Way, a light beam would need 100,000 years. The The solar neighborhood, seemingly vast to us, is but a tiny fraction of this spiral city of stars. And yet, within this small neighborhood, the universe teaches patience, perspective, and awe. So tonight, as you rest beneath the stars, let yourself feel the quiet vastness of the solar neighborhood. You are not simply an observer. You are a participant in this cosmic dance. Every planet, every asteroid, every distant star exerts a silent influence, shaping the rhythms of our home. And when you look up at the night sky, you are seeing not only the light from distant suns, but the glow of your own existence reflected across space and time. The solar neighborhood is our first step into understanding the vastness of the universe. Here, distances are immense, yet familiar. Here, stars and planets form a community in which we find our place. And from this intimate perspective, we are ready to expand outward, to venture beyond these nearby suns, to glimpse the full immensity of the galaxy itself. Take one last look at the night sky from this vantage, breathing in the calm, letting the enormity settle gently in your mind. The solar neighborhood is vast, serene, and alive, and within it, you are both small and infinitely connected. With this understanding, the universe begins to unfold, layer by layer, star by star, mystery by mystery. Beyond the gentle orbits of planets and the quiet passage of nearby stars lies a grander stage, a vast cosmic city stretching across unimaginable distances, the Milky Way galaxy. Our solar neighborhood is a tiny, unassuming street within this sprawling metropolis of stars, yet it is home, a place we understand in small, intimate ways. To grasp the universe's immensity, we must first linger in this galactic home, tracing its spiral arms, its dense cores, and the countless stars that dwell within it. The Milky Way is a spiral galaxy, a luminous pinwheel rotating gracefully in the darkness of space. From our vantage on Earth, it appears as a hazy band of light stretching across the night sky, soft and diffuse, yet hinting at the billions of stars packed tightly together in its plane. This luminous band is only the tip of the iceberg, a glimpse of the immense structure that lies beyond what our eyes can fully perceive. Our solar system rests in a quiet suburb of the galaxy, a region known as the Orion Arm. Here, stars drift lazily in vast arcs around the galactic center, their motions guided by the unseen hand of gravity. From our perspective, the galaxy feels stable, eternal, yet in reality, it is alive, dynamic, a swirling sea of matter and energy, constantly evolving over millions of years. At the heart of the Milky Way lies the galactic core, a dense congregation of stars and clouds of gas, packed into a volume so small that the brightness is almost blinding when observed in certain wavelengths. Hidden there is a supermassive black hole, Sagittarius A, a gravitational anchor around which the entire galaxy revolves. Though invisible directly, its presence is undeniable, shaping the orbits of nearby stars and influencing the flow of gas and dust in the central bulge. The core is a place of extremes, where stellar densities are millions of times higher than in our solar neighborhood. And yet, even here, life continues quietly on distant worlds in the galaxy's calmer outskirts. As we drift outward from the center, the spiral arms unfurl like delicate ribbons, home to clusters of young, bright stars, glowing nebulae, and vast clouds of molecular gas. These arms are stellar nurseries, places where gravity weaves the cosmic fabric into new suns and new worlds. Some stars in these regions shine with such intensity that their light can outshine entire neighborhoods of older, smaller stars. Yet they are fleeting, living brilliant but short lives before exploding as supernovae, seeding the galaxy with elements forged in their fiery cores. The Milky Way is not a uniform city. Its density varies dramatically. In the galactic plane, stars are packed relatively closely, each moving along its orbit in a careful dance choreographed by gravity. Above and below the plane, stars become sparse, scattered like glitter in a dark ocean. Between the arms, vast voids of interstellar space stretch endlessly, filled with tenuous gas, and occasional wandering stars, places almost eerily quiet, almost completely empty by comparison. Take a moment to imagine the scale. Our solar system is about 8 light minutes across, small, intimate. The nearest star, a neighbor, is 4 light years away. And yet the Milky Way stretches approximately 100,000 light years from one end to the other. Traveling at the speed of light, it would take 100,000 years to cross from one side to the other. Within this expanse lie hundreds of billions of stars, each with its own potential systems of planets, moons, comets, and perhaps life. Clusters of stars gather in glimmering pockets known as open clusters, often less than a few hundred light years across, young and dynamic, their stars tightly bound for a few 100 million years before drifting apart. Globular clusters, on the other hand, are ancient and massive, densely packed with hundreds of thousands of stars orbiting the galaxy's halo. These clusters are relics of the Milky Way's early days, remnants of a time when the galaxy was still forming, still gathering its stars like droplets, collecting to form a river. Between the stars lies a network of dust and gas. Though mostly invisible to the naked eye, these interstellar clouds play a crucial role in the galaxy's life cycle. They are the cradles of star formation, collapsing under gravity to ignite new suns. They absorb and scatter light, giving the Milky Way its dark, intricate patterns when seen in long exposures. Without them, the galaxy would appear stark and empty, devoid of the complex structures that give it beauty and meaning. The stars themselves vary widely, from tiny red dwarfs that burn slowly and quietly for trillions of years, to massive blue giants that shine with incredible intensity before ending in spectacular supernova. Every star has a story, a life cycle, and a role in the galactic ecosystem. Planets may form around some, others may harbor no worlds at all. The diversity is staggering, reminding us that the Milky Way is not a static backdrop, but a living, breathing entity, constantly evolving. Gravity is the invisible glue holding this vast city together. It shapes orbits, guides stars along their paths, and binds clusters into the larger galactic structure. Yet gravity also permits chaos. Stars occasionally collide or pass close enough to disturb planetary systems. Gas clouds are compressed or shredded, triggering bursts of star formation or sending shockwaves across space. The galaxy is both orderly and wild, a place of serene motion and violent creation. From Earth, the Milky Way seems close, a band of light across the sky. But in reality, it is immense, our sun a mere pinpoint among billions. Each night, we see only a fraction of its glory, and even our most powerful telescopes can barely capture the full scale. The true majesty lies in its three-dimensional structure, in the spirals that curl elegantly around the center, in the halo of stars that stretches far above and below the plane, and in the invisible web of dark matter that holds it all together. The Milky Way is not alone. It exists in a neighborhood of galaxies, a cosmic community known as the local group. And yet, within this galaxy, every planet, every star, and every piece of gas has its place, its motion, its purpose. It is a home, both vast and intimate, a reminder of the grandeur that surrounds our solar neighborhood. As you contemplate the Milky Way tonight, allow yourself to drift along its spiral arms, to follow the orbit of the sun, to feel the slow, majestic rotation that has been ongoing for billions of years. Think of the light that has traveled thousands of years to reach your eyes, the echoes of distant stars illuminating your imagination. This galaxy is enormous, yet it is your home, the stage upon which the story of your sun and your own existence unfolds. Every nebula, every cluster, every star is a note in a cosmic symphony, each playing its part in the galaxy's ongoing song. The Milky Way is alive in time, ancient beyond measure, yet still creating, still evolving, still expanding the possibilities of life, light, and matter. It is here, within this spiral city of stars, that we begin to truly appreciate the scale of the universe, a scale so vast that it can humble the imagination and inspire awe at every turn. So pause beneath the night sky, letting your mind drift along the Milky Way's arms. Feel the quiet majesty of billions of stars moving in silent harmony. Know that you too are part of this galaxy, a traveler in a tiny solar system, drifting through a spiral of light and gravity. From this perspective, the universe becomes tangible, vast yet intimate, a home that stretches across unimaginable distances, inviting curiosity, reflection, and wonder. As we drift outward from the Milky Way, the familiar spiral arms fade into the vastness of space, and we begin to see the galaxy not as an isolated island, but as a member of a greater cosmic community. This neighborhood of galaxies is known as the local group, a sprawling assembly of more than 50 galaxies bound together by gravity, each with its own history, its own stars, and its own stories. Here, the scale of the universe begins to stretch beyond comprehension, and we start to glimpse the immensity that surrounds our tiny solar system, and even our grand Milky Way. The local group is dominated by three giants: the Milky Way, our spiral home; Andromeda, the closest spiral galaxy to us and larger in size and mass; and the Triangulum galaxy, smaller but still significant. These galaxies, though separated by millions of light years, interact in subtle and profound ways. Their gravitational pull influences the motion of smaller satellite galaxies, tiny dwarfs that orbit their larger neighbors like moths around distant radiant lamps. Andromeda, or M31 as astronomers call it, is a spiral similar to the Milky Way, but with perhaps 1 trillion stars, nearly twice the mass of our galaxy. On a clear, dark night, it appears as a faint smudge in the sky, barely perceptible to the unaided eye. Yet it is a colossal system, a city of stars whose outermost edges reach nearly 220,000 light-years from its center. Over the next several billion years, Andromeda and the Milky Way will begin a slow, inevitable dance, moving toward a collision that will eventually merge them into a single, larger galaxy, a cosmic embrace that will last for billions of years. Triangulum, though smaller, is no less fascinating. Its spiral arms are tightly wound, and it hosts regions of active star formation, glowing with the light of young, hot stars. Even its modest size compared to the Milky Way does not diminish its role in the local group. Triangulum may serve as a future participant in the Milky Way-Andromeda merger, its stars potentially absorbed into the grand new galaxy that will emerge from this titanic interaction. Beyond these giants lie countless smaller galaxies, dwarf ellipticals, irregulars, and faint, almost invisible companions that drift silently in the gravitational currents of the local group. Many of these are so dim that they were only recently discovered, hidden in plain sight by their faint light and small size. Yet each is a world of stars, perhaps with planets and gas clouds, each with its own quiet story of formation, evolution, and eventual fate. The local group itself spans roughly 10 million light-years in diameter, a modest size by cosmic standards, yet still unimaginably vast to our human minds. Within this volume, galaxies move, orbit, and interact. Gravity pulls them together, while the expansion of the universe tugs them apart, a delicate balance between cohesion and dispersion. This tug-of-war shapes the structure of the universe on scales far beyond our everyday experience, influencing the formation of galaxy clusters and superclusters. Our perspective begins to shift as we consider the sheer number of stars contained in the local group. The Milky Way alone hosts hundreds of billions of stars. Andromeda exceeds 1 trillion. When combined with all the smaller galaxies, the local group contains well over 2 trillion stars, each potentially a sun to distant planets, each a tiny beacon of light in the darkness. Yet even this immense collection is just a drop in the ocean compared to the universe beyond. Clusters of galaxies begin to emerge as the next level of cosmic organization. While the local group is a modest gathering, larger assemblies called galaxy clusters contain thousands of galaxies bound together. Gravity becomes a master architect on these scales, sculpting the distribution of matter over millions of light years. Some of the nearest clusters, such as the Virgo cluster, contain thousands of galaxies, each spinning, colliding, and evolving over eons. The distances between galaxies are staggering. Even within the local group, Andromeda is approximately 2.5 million light-years from the Milky Way. Light traveling from one to the other takes 2.5 million years to cross the intervening void. Imagine sending a signal today. It would arrive in the distant past, long before humanity existed. These distances challenge our perception of space and time, reminding us that even our most immediate cosmic neighbors exist in a realm beyond ordinary human experience. Gravity binds these galaxies together, but the universe itself is expanding. While the local group is gravitationally bound and will remain a cohesive unit for billions of years, more distant galaxies are receding from us. The further a galaxy lies, the faster it seems to move away, a motion discovered by Edwin Hubble in the early 20th century. This expansion stretches the very fabric of space, carrying galaxies apart at speeds that can exceed the speed of light when viewed over vast distances, creating a cosmic horizon beyond which we cannot see. Between galaxies lies intergalactic space, vast expanses of emptiness that are far from empty. Thin clouds of hydrogen and helium drift through these voids, remnants of the Big Bang that permeate the universe. Invisible dark matter weaves through this cosmic web, its gravity shaping the distribution of galaxies and clusters, holding the universe's large-scale structure together like a skeleton supporting a vast, luminous organism. Cosmic filaments connect clusters and groups, forming a web-like structure that stretches across hundreds of millions of light years. Galaxies congregate along these filaments, while enormous voids lie between them, regions of almost complete emptiness, spanning tens of millions of light years. The universe on these scales is a tapestry of structure and emptiness, a pattern repeating itself across unimaginable distances. As we look beyond the local group, we see the beginnings of the observable universe itself, a vast expanse filled with billions of galaxies, each a city of stars. Every galaxy, from the smallest dwarf to the mightiest spiral, participates in a cosmic dance choreographed by gravity and time. Each star contributes to the light that reaches us, carrying information across the void, telling the story of creation, evolution, and eventual decay. Contemplating the local group and the structures beyond forces a sense of humility. Our solar system, immense in human terms, is but a tiny speck in a galaxy of billions of stars. Our galaxy, grand and majestic, is but one among many, a single member of a modest cluster in a universe that extends across billions of light years. And yet, it is precisely within this tiny corner of the cosmos that we exist, that we observe, and that we begin to understand the vast, intricate structure of the universe. The local group and the galaxies beyond invite us to consider our place in the cosmos, not as a center, but as a participant in a vast, unfolding story. Every galaxy has its own path, every star its own life, and every planet its own potential. The distances and scales involved are almost impossible to comprehend, yet they offer a perspective both humbling and exhilarating. And as we gaze outward, the universe continues to reveal itself in layers. The Milky Way, the local group, galaxy clusters, filaments, and voids. Each layer unfolds into the next, expanding our understanding, stretching our imagination, and revealing the profound immensity of the cosmos. We are travelers on a tiny ship, drifting through an ocean of galaxies, bound by gravity, yet carried forward by time. And it is here, in this vast cosmic sea, that we begin to sense the full scale of the universe, a scale that defies comprehension, yet invites endless wonder. Beyond the modest gathering of the local group lies a grander and more imposing structure, galaxy clusters. These are cosmic cities on a scale that boggles the mind, sprawling assemblies of thousands of galaxies bound together by gravity, each galaxy spinning and evolving in a complex dance, its stars, gas, and dark matter weaving together into a cosmic tapestry. In these clusters, the universe's architecture begins to take shape, revealing the patterns that define the very skeleton of the cosmos. Galaxy clusters are immense. A typical cluster spans millions of light years, a volume so vast that light itself takes millions of years to traverse it. Within these clusters, galaxies are not randomly scattered, but arranged in intricate patterns, influenced by the invisible hand of gravity and the pervasive presence of dark matter. The most massive clusters can contain thousands of galaxies, with masses reaching 1,000,000 billion times that of our Sun. These are the titans of the cosmos, massive enough to warp space and influence the motion of other clusters, even over distances of tens of millions of light years. The galaxies within a cluster come in many forms. Spirals, like the Milky Way and Andromeda, coexist with massive elliptical galaxies, swollen and ancient, their stars aged and quiet. Dwarf galaxies dart between these giants, their faint light often overwhelmed by the cluster's luminescent heart. Interactions and collisions are common here, shaping galaxies over billions of years. When two galaxies collide, their stars rarely meet, but their gas clouds crash together, sparking bursts of star formation, igniting brilliant nurseries that shine across millions of light years. These interactions are both violent and transformative, a cosmic choreography that reshapes the very structure of galaxies. At the heart of many clusters lies a brightest cluster galaxy, BCG, a colossal elliptical so large that it dwarfs even the Milky Way. These galaxies are ancient, their stars formed in the earliest epochs of the universe. Surrounding them is a hot, diffuse plasma, glowing in X-ray light, invisible to the naked eye, but detectable by telescopes designed to see the universe beyond visible wavelengths. This intracluster medium contains more mass than the stars themselves. A turbulent sea of charged particles heated to tens of millions of degrees by the gravitational energy of the cluster. Clusters are not isolated. They are the nodes in a vast cosmic web, connected by filaments of galaxies, gas, and dark matter, stretching across hundreds of millions of light years. These filaments act as the highways of the universe, guiding the motion of galaxies and feeding clusters with matter. Between the filaments lie enormous voids, regions almost entirely empty of galaxies, spanning tens of millions of light years. The contrast between the dense filaments and the immense emptiness of voids creates a web-like structure that defines the universe on its largest scales. This cosmic web is not static. It evolves over time. Gravity pulls matter along filaments toward nodes, feeding clusters and creating larger and more massive structures. Over billions of years, clusters merge, forming superclusters, vast regions containing tens of thousands of galaxies. The largest known supercluster, the Laniakea supercluster, which contains our Milky Way, spans over 500 million light-years and contains hundreds of thousands of galaxies. To imagine such a scale is to confront the limits of human comprehension. Our galaxy, immense as it feels, is just a tiny part of a structure so vast that light takes hundreds of millions of years to cross it. Observing galaxy clusters also reveals the mysterious influence of dark matter. Visible matter, the stars, gas, and dust we can detect, accounts for only a fraction of a cluster's total mass. The remainder is an invisible substance, dark matter, whose gravitational pull shapes the motion of galaxies and the cluster itself. Without dark matter, these clusters would not hold together. Galaxies would drift apart, unbound, and the cosmic web would unravel. Though we cannot see dark matter directly, its presence is inferred through the motion of galaxies and the bending of light, a phenomenon known as gravitational lensing. In this way, the universe's invisible scaffolding becomes visible, hinting at a deeper, hidden order underlying the apparent chaos. Within clusters, galaxies evolve more rapidly than in isolation. The dense environment strips gas from galaxies, slowing star formation and transforming young blue spirals into older red ellipticals. Collisions are frequent, mergers inevitable, and over billions of years, clusters grow more concentrated. They're galaxies settling into a dynamic equilibrium, a delicate balance between gravity's pull and the expansion of space. Observing these processes allows astronomers to study galaxy evolution on scales impossible within a single galaxy, providing a window into the past and a prediction for the future. Clusters are also laboratories for extreme physics. The hot intracluster medium emits X-rays, detectable across vast distances. Shock waves from galaxy collisions ripple through the plasma, and relativistic particles spiral along magnetic fields, producing radio waves that echo across millions of light years. Black holes at the centers of massive galaxies influence the cluster's dynamics, launching jets of energy that can heat or displace gas, regulating star formation. In every way, clusters are cosmic engines, churning matter, energy, and light on incomprehensible scales. Beyond the clusters lie superclusters and the even grander scale of the cosmic web. Superclusters are vast assemblies of clusters and groups, often elongated and filamentary, connected by the same structures that shape individual clusters. The Laniakea supercluster, which contains the Milky Way, is just one among millions, each a sprawling expanse of matter and galaxies. Within these superclusters, galaxies trace the threads of the cosmic web, their motion dictated by gravity and the distribution of dark matter. The universe on these scales resembles a vast network of filaments and nodes, a luminous web suspended in the darkness. Yet even this immense structure is but a fraction of the observable universe. Beyond superclusters, galaxies continue to stretch outward, receding from us at ever-increasing speeds due to the expansion of space itself. The cosmic microwave background, the faint afterglow of the Big Bang, reminds us of the universe's origin, a time when matter, energy, space, and time were compressed into a dense, hot state. The universe has been expanding ever since, carrying galaxies along in its silent, inexorable flow. Contemplating galaxy clusters and the cosmic web evokes a profound sense of scale and interconnectedness. Each galaxy, each star, each planet is part of an immense network, bound by gravity, shaped by the invisible hand of dark matter, and stretched across billions of light years by the expansion of space. Our Milky Way, our solar system, even our fragile, fleeting existence on Earth is part of this vast tapestry. We are, in a sense, travelers within a structure of unfathomable magnitude, moving along filaments that trace the history of the universe itself. And as we gaze deeper into the universe, we realize that our understanding is still incomplete. For every galaxy we observe, there may be countless others hidden beyond the limits of detection, invisible in the darkness, receding faster than light, unreachable by any signal. The universe is not only immense, it is unbounded in its possibilities, a place where matter, energy, and the laws of physics interact to create an infinite variety of structures, scales, and phenomena. Galaxy clusters, superclusters, and the cosmic web are more than just collections of matter. They are the veins of the universe, carrying energy, matter, and information across incomprehensible distances. They are the framework upon which all cosmic history is written, a record of the past, a guide to the future, and a reminder that in the vastness of space, everything is connected. As we continue our journey outward, beyond the local group and its modest companions, through clusters and superclusters, we begin to sense the full majesty of the universe's architecture. The scales are staggering, the distances unimaginable, yet the patterns repeat, revealing a harmony underlying the chaos. The universe is both immense and ordered, vast and structured, a cosmic symphony playing out over billions of years. And so we drift further, carried along the filaments of the cosmic web, observing galaxies and clusters, marveling at the invisible forces that hold them together, and sensing, perhaps for the first time, the full immensity of the universe in which we reside. The journey has only begun, but already the scale of the cosmos stretches our minds and ignites our imagination. A reminder of the infinite, wondrous complexity that surrounds us. As we journey further outward from the cosmic web, past the great clusters and superclusters, we encounter a phenomenon that defines the universe itself, its expansion. Space is not static. It stretches, flows, and grows, carrying galaxies along in a silent, relentless motion. This expansion is not like motion through space. It is space itself growing, stretching the distances between galaxies, subtly at first, imperceptibly at human scales, but over millions and billions of light years, it becomes the dominant feature of the cosmos. The discovery of cosmic expansion is one of the most profound revelations in modern astronomy. In the early 20th century, astronomers observing distant galaxies noticed a curious pattern. Nearly all galaxies appeared to be moving away from us. Their light was shifted toward the red end of the spectrum, a phenomenon known as redshift. The farther a galaxy was, the faster it seemed to recede. It was as if the universe itself were stretching, carrying its contents along like raisins in a rising loaf of bread. This observation, later formalized as Hubble's law, revealed that the universe had a dynamic history, that space itself was growing over time. It implied a past in which all matter was concentrated in a dense, hot state, a moment we now call the Big Bang. From that initial explosion of energy and matter, space has been expanding for nearly 13.8 billion years, creating the vast cosmic distances we now observe. Cosmic expansion has profound implications for our understanding of distance and time. The light from distant galaxies does not travel through a fixed void. It traverses a stretching space. When we look at a galaxy a billion light years away, we are not merely seeing light that has traveled a billion years through space. We are observing an object that was much closer when that light began its journey, yet now resides far beyond its original location, carried by the expanding fabric of the cosmos. This expansion also defines the limits of what we can observe. The universe is vast, but only a portion of it is visible to us, the observable universe. Its radius is roughly 46 billion light years, far larger than the universe's age might suggest, because space itself has been stretching while light travels. Beyond this boundary, light has not had time to reach us since the Big Bang, and so these regions remain forever hidden, unreachable, and unknown. Within the observable universe, galaxies continue to recede at tremendous speeds. Distant galaxies, billions of light years away, may be moving faster than the speed of light relative to us, not violating relativity, because it is space itself that is expanding. This means that over time, more and more galaxies will disappear beyond our cosmic horizon, leaving behind only local structures, clusters, and superclusters bound tightly enough by gravity to resist the expansion. The universe is slowly isolating itself, a process that will unfold over tens of billions of years, shrinking the observable cosmos for any distant observer. Cosmic expansion is also intimately tied to a mysterious component known as dark energy. Observations of distant supernovae in the late 20th century revealed that the universe's expansion is not slowing down, as might be expected from gravitational attraction, but accelerating. Dark energy, pervasive and invisible, seems to push space outward, overwhelming gravity on the largest scales. Its nature remains one of the greatest mysteries of modern physics, yet its effects are undeniable. It governs the ultimate fate of galaxies, clusters, and the universe itself. The interplay between expansion and structure is fascinating. On small scales, gravity dominates. Stars orbit within galaxies, galaxies within clusters, and clusters within superclusters, forming bound systems. But on the grandest scales, expansion dominates, separating structures and shaping the universe's large-scale geometry. Observing this balance allows astronomers to measure fundamental parameters, such as the Hubble constant, the density of matter, and the properties of dark energy, all of which inform our understanding of the universe's past and its future trajectory. Looking deeper, we realize that cosmic expansion also stretches light itself. The further away a galaxy is, the longer its light has been traveling, and the more space has expanded during that journey. This stretches the wavelengths of light, shifting it toward the red. For the most distant galaxies, this redshift is extreme, moving visible light into the infrared and making these ancient galaxies detectable only by specialized instruments. By studying redshift, astronomers can peer back in time, observing the universe when it was a fraction of its current age, revealing the birth of the first stars and galaxies. The observable universe is not uniform, yet it is surprisingly homogeneous on the larger scales. Galaxies cluster and filament in some regions, while immense voids span tens or even hundreds of millions of light years in others. Yet, if we step back and consider scales of billions of light years, the distribution of matter becomes remarkably smooth, echoing the conditions of the early universe as revealed by the cosmic microwave background, the faint afterglow of the Big Bang. This balance between local complexity and large-scale uniformity is one of the universe's most elegant features. Time itself is intertwined with expansion. As space stretches, the universe cools. From an initial temperature of billions of degrees, the universe has cooled to just 2.7 Kelvin, a near absolute zero glow detectable only in microwave wavelengths. This cooling governs the formation of atoms, molecules, stars, and galaxies, shaping the evolution of cosmic structures over billions of years. Expansion is thus not merely a spatial phenomenon, it is also a temporal one, entwining distance, time, and the evolution of matter in a single grand narrative. Our solar system, our galaxy, our local group, all reside within this expanding cosmos, carried along by the silent flow of space. While locally bound structures resist expansion, on cosmic scales, everything is moving apart. The Milky Way and Andromeda, destined to collide in about 4 billion years, will form a new galaxy. Yet beyond this local interaction, the universe continues to stretch, carrying distant clusters away, isolating us within an ever-expanding void. Beyond the observable horizon, the universe may extend infinitely, or it may have a structure we cannot perceive. Cosmologists model the universe using general relativity, observing the curvature of space and the distribution of matter. Current evidence suggests a flat, infinite cosmos, though the true extent remains unknown. Every galaxy we see is just a tiny window into an immeasurable expanse, a reminder that our perspective is necessarily limited, yet rich with information. The observable universe contains roughly 2 trillion galaxies, each with hundreds of billions of stars, stretching across a vast canvas, 92 billion light-years in diameter. It is a realm where light from the earliest galaxies travels billions of years to reach us, where cosmic expansion continuously reshapes distances, and where dark energy drives the ultimate acceleration of space. In contemplating this scale, we are confronted with both awe and humility. The universe is immense beyond imagination, and yet, within it, we have the tools to uncover its deepest secrets. Cosmic expansion also raises profound philosophical questions. If galaxies are disappearing beyond our horizon, what will a distant observer see? In a future eon, observers might perceive a universe almost empty, unaware of the vast structures that exist today. The universe's observable limits are not just a scientific boundary. They define the scope of knowledge itself, reminding us that our understanding is always framed by perspective, scale, and time. Despite its enormity, the observable universe is a tapestry of patterns and order. Its expansion, far from being chaotic, follows predictable laws. Its structures, from filaments to superclusters, arise from gravity and the primordial distribution of matter. Its evolution, governed by the interplay of matter, radiation, dark matter, and dark energy, forms a narrative spanning billions of years. In this vastness, we are both observers and participants, tracing the history of light, matter, and space as they unfold across incomprehensible distances. And so, as we drift along the edge of the observable universe, carried by the expansion of space itself, we sense the immensity of all that lies beyond. we glimpse a cosmos not static, but alive with motion, growth, and change. Galaxy clusters recede, filaments stretch, and voids widen, all as part of a single silent symphony. Each photon that reaches us is a messenger from the past, a signal from a time long ago, illuminating a universe whose scale dwarfs imagination and challenges comprehension. The universe, expanding and ever-changing, stretches our minds as much as it stretches space. It invites us to consider the unimaginable distances, the invisible forces, and the cosmic timeline that connects us to the earliest epochs. The observable universe is vast, but it is only the beginning of understanding the universe as a whole, a universe in motion, boundless in scale, and filled with structures both luminous and hidden, stretching outward to infinity, or at least to a distance forever beyond our reach. As we drift ever outward through the cosmos, carried by the gentle expansion of space, we eventually reach the limits of what is visible to us, the edge of the observable universe. This boundary is not a wall, nor a sudden drop into emptiness. It is a horizon defined by time, distance, and the speed of light. Beyond it lies the unknown, a realm that no photon has yet reached us from, a silent expanse that stretches into infinity, or perhaps bends in ways we cannot perceive. The observable universe, roughly 92 billion light-years across, is defined by the distance light has traveled since the beginning of the cosmos. It is a time capsule, each photon a messenger from the past, carrying information from galaxies as they were billions of years ago. But light from regions beyond this horizon has not yet had time to reach us, and due to cosmic expansion, some regions may never be observable. This edge, the cosmic event horizon, represents the ultimate boundary of human observation, the limit where knowledge and mystery meet. As we approach this horizon, we encounter galaxies whose light has traveled for more than 13 billion years. Their images are faint, redshifted into infrared, stretched by the expansion of space, revealing the universe in its infancy. These primordial galaxies formed when the cosmos was a fraction of its current age, when stars were few and small, and the first heavy elements had yet to emerge. Observing them is like looking through a keyhole into the earliest chapters of cosmic history. Beyond these observable galaxies, the universe continues, yet we cannot see it. Cosmologists theorize that space stretches on, perhaps infinitely, filled with structures similar to those we know. Galaxies, clusters, and superclusters forming cosmic filaments across a vast expanse. If the universe is infinite, then beyond the observable horizon lies an unending tapestry, indistinguishable from what we can see except for the fact that its light has not yet reached us. The concept of the multiverse also arises when contemplating what lies beyond. Some theories suggest that our universe might be one of many, a single bubble in a vast cosmic foam. Beyond our horizon, other regions may exist with different physical laws, different constants, and entirely different histories. These possibilities challenge the very definition of universe and stretch the imagination further than any distant galaxy. Cosmic inflation, the rapid expansion that occurred in the first fractions of a second after the Big Bang, provides insight into the vastness beyond the observable universe. During inflation, space expanded exponentially, stretching regions far beyond our current horizon. The observable universe is a tiny patch of this immense inflationary fabric. If inflation continues beyond our view, then most of the universe lies forever beyond our reach, hidden not by walls, but by distance and the finite speed of light. This edge is also a reminder of time's passage. Every photon from distant galaxies carries not only distance information, but also temporal information. When we observe a galaxy at the cosmic edge, we are seeing it as it was billions of years ago, a moment frozen near the dawn of time. Beyond the observable boundary, time itself continues, galaxies evolve, stars are born and die, yet we remain unable to witness these events. The universe stretches infinitely, and time marches onward, unobserved and unrecorded by any observer within our cosmic bubble. The expansion of space shapes the horizon itself. Due to dark energy, the universe's expansion is accelerating. This means that some galaxies currently observable will eventually cross the event horizon, disappearing from view forever. Over unimaginable timescales, the observable universe will shrink in terms of visible structures, leaving only the gravitationally bound galaxies of our local group. The edge, therefore, is not static. It shifts with time, an ever-changing boundary that defines the limits of observation. Cosmic microwave background radiation, CMB, offers another glimpse toward this horizon. The CMB is the afterglow of the Big Bang, light that has traveled nearly 13.8 billion years to reach us. It provides a map of the universe at a mere 380,000 years old, revealing density fluctuations that seeded galaxy formation. Beyond the CMB, the universe existed in a plasma state, opaque to light. We cannot see beyond it directly, but subtle clues in polarization and gravitational effects allow cosmologists to infer the structures that lie further out. Gravitational waves also hint at the universe beyond direct observation. These ripples in space-time, caused by cataclysmic events like merging black holes, travel unimpeded across the cosmos. Unlike light, they can penetrate regions opaque to photons, offering a unique window into events far beyond the reach of traditional telescopes. They remind us that even at the cosmic edge, nature provides indirect ways to probe the unknown, teasing out information from regions we cannot see. Beyond the observable universe, the large-scale structure may mirror the patterns we know, filaments, voids, and clusters forming a cosmic web across unimaginable distances. Yet subtle differences may exist. Slight variations in density, initial conditions, or the influence of dark energy could make these regions different from our local cosmos. The further we imagine, the more the universe transforms from a familiar landscape into a vast alien expanse. Mathematics and theoretical physics become our guides here, for observation reaches its limit. Models of inflation, dark energy, and general relativity allow scientists to extrapolate beyond the horizon. These models suggest a universe far larger than what we can see, perhaps even infinite. Yet these predictions remain tentative, constrained by assumptions about uniformity and the laws of physics that we know. The universe beyond observation is both constrained and unknowable, a paradox that fuels exploration and imagination. As we contemplate the edge, the scale of the unknown dwarfs comprehension. Every star, every galaxy, every cosmic filament we can observe is but a minuscule fraction of the greater cosmos. Beyond our sight lies a vastness so immense that even the concept of distance becomes abstract. Light years, once staggering, are insufficient to describe the expanse that stretches silently into infinity. The edge of the observable universe is a boundary of knowledge, a place where curiosity meets limitation. Philosophically, this edge inspires reflection. What does it mean for humanity that so much of the cosmos is forever beyond perception? How do we reconcile our smallness with the enormity of the universe? And yet, in observing even a tiny fraction of it, we glimpse profound patterns, understand cosmic history, and trace the story of matter from the first instance of time. The unknown does not diminish our understanding. It frames it, reminding us of both humility and possibility. The edge of the observable universe also connects to the concept of causality. Events beyond the horizon cannot influence us because their light, or any signal, has not yet reached us. The universe is effectively segmented into causally connected regions, each with its own horizon. What occurs beyond these limits unfolds independently, a realm of reality that exists but remains inaccessible to observation. The cosmos, therefore, is not only vast in space, but compartmentalized in terms of cause and effect. Despite the limits of observation, the universe beyond continues its evolution. Stars form and die, galaxies collide and merge, and black holes grow silently in the depths of space. Inflationary theory suggests that entire regions may undergo transformations we cannot even conceive. Perhaps new universes bubble into existence, disconnected from ours, or quantum fluctuations seed new cosmic domains. Each of these possibilities stretches the imagination, revealing a cosmos as limitless in potential as it is in scale. Yet even as we contemplate infinity, the edge reminds us of the value of what we can observe. Every photon from a distant galaxy, every particle of the cosmic microwave background, every gravitational wave carries information about the universe's history. By studying the observable portion, we reconstruct the story of space, time, and matter, connecting our small, fleeting existence to the grand narrative of the cosmos. Thus, at the edge of the observable universe, we stand at the threshold of knowledge. Beyond lies the unknown, stretching into a realm that may be infinite, or at least immeasurable. Galaxies, structures, and entire cosmic landscapes exist there, silent and invisible, yet part of the same fabric of space-time. The boundary is not a wall, but a horizon, ever expanding, shifting with time, and challenging the limits of perception, imagination, and understanding. Here, at this cosmic frontier, the universe both humbles and inspires. It reminds us that no matter how far we look, there is always more beyond, a realm of endless possibilities and mysteries that beckon exploration. The edge of the observable universe is not a conclusion, but an invitation to imagine, to theorize, and to continue seeking knowledge, even in places where light has yet to arrive. As we peer deeper into the cosmos, following the faint glimmers of distant galaxies and the glowing threads of interstellar gas, a silent mystery becomes ever more apparent. The universe is far heavier than it appears. The stars, planets, and luminous clouds of gas that light up the night sky account for only a fraction of the cosmos. Beneath this luminous veneer lies a vast unseen structure, an invisible scaffolding that shapes the motions of galaxies and the formation of cosmic filaments. This is the realm of dark matter, a shadowy presence whose existence is inferred from its gravitational fingerprints rather than direct observation. Dark matter is, in essence, the hidden skeleton of the universe. It neither emits nor absorbs light, remaining invisible to telescopes and invisible to all forms of electromagnetic radiation. Yet its presence is undeniable. Galaxies rotate with astonishing speed, their outer stars moving far faster than the visible mass can account for. Without the gravitational tug of unseen matter, these galaxies would fly apart, stars escaping into the void. Dark matter provides the necessary glue, an invisible hand holding the cosmic structures together. To understand its significance, imagine a spider's web stretching across the vastness of space. The luminous galaxies, brilliant and radiant, cling to the strands, tracing the invisible threads that weave the cosmic web. Dark matter forms the framework of this web, shaping the growth of galaxies and clusters over billions of years. Regions dense with dark matter become cosmic hubs, attracting gas and dust, igniting star formation, and nurturing galaxies that shine across the universe. In the emptier regions, the lack of dark matter creates cosmic voids, vast expanses where few stars reside, stretching like silent gulfs between the filaments. The search for dark matter has been one of the most profound quests in modern astrophysics. Although we cannot see it directly, scientists detect it through its gravitational influence. Galaxies within clusters orbit faster than their visible mass allows. Gravitational lensing, the bending of light around massive objects, reveals distortions that betray the presence of hidden mass. In clusters of galaxies, the luminous matter is only a small fraction of the total gravitational pull observed. Each observation, each measurement, reinforces the notion that dark matter dominates the universe's mass budget, outnumbering normal matter by nearly 5-1. Yet what is dark matter made of? This question remains one of the great enigmas of science. Candidates abound, from weakly interacting massive particles, WIMPs, to sterile neutrinos, yet none have been confirmed. It is not baryonic matter. the ordinary atoms that form stars, planets, and humans, but something more elusive. Its interactions with normal matter are subtle, detectable only through the faintest gravitational effects or the rarest particle collisions in carefully shielded detectors deep underground. The importance of dark matter extends far beyond individual galaxies. On the grandest scales, it orchestrates the cosmic web itself. Computer simulations, seeded with small density fluctuations observed in the cosmic microwave background, show that dark matter collapses into filaments, sheets, and nodes, guiding the formation of galaxies and clusters. The luminous universe, the galaxies we observe, emerges as a consequence of this invisible structure. Without dark matter, the cosmos would look very different. Galaxies would be smaller, less clustered, and star formation might have proceeded far more slowly. Interestingly, dark matter is not evenly distributed. Some regions are dense, forming massive halos around galaxies and clusters, while others are sparse, creating voids where little forms. These variations influence cosmic evolution in subtle yet profound ways. The Milky Way itself resides within a halo of dark matter, a vast spherical cocoon extending far beyond the visible stars, enveloping our solar system in a silent, invisible mass. It is this halo that keeps our galaxy coherent, preventing it from tearing apart as stars orbit the galactic center. While dark matter dominates gravity on cosmic scales, it remains non-interactive in other ways. It does not cool, condense, or form stars. It passes through itself and ordinary matter largely unaffected, leaving the luminous universe to evolve independently within its invisible scaffolding. In this sense, dark matter is both architect and silent observer, shaping the universe while remaining untouched by the chaos of light and heat. The search for dark matter has driven remarkable technological innovation. Detectors deep underground aim to capture the rare interactions between dark matter particles and ordinary matter, shielded from cosmic rays and background noise. Telescopes survey the sky for gravitational lensing effects, mapping the distribution of invisible mass across cosmic filaments. High-energy particle colliders attempt to recreate conditions of the early universe, hoping to produce dark matter in miniature flashes of energy. Each approach pushes the boundaries of human ingenuity, seeking to illuminate the darkness that underpins all cosmic structures. Dark matter also ties directly into the universe's ultimate fate. It contributes to the total density of the cosmos, influencing whether space will continue expanding indefinitely, slow, or eventually collapse. Alongside dark energy, the mysterious force driving accelerated expansion, dark matter defines the cosmic balance. Its gravitational pull resists expansion locally, while dark energy stretches space globally. Together, these hidden forces dictate the rhythm of cosmic evolution, from the smallest galaxies to the largest superclusters. Cosmologists often describe dark matter as a cosmic sculptor. In the early universe, small quantum fluctuations in density were magnified by gravity, with dark matter serving as the principal actor. Ordinary matter, interacting with radiation, was delayed in collapsing, but dark matter, unaffected by photons, began clumping immediately. These clumps became seeds for galaxy formation, guiding the growth of structures we now observe. Without dark matter, the universe would lack its intricate web of filaments, clusters, and voids. The visible universe is, in essence, a shadow of the invisible. The mystery deepens when we consider the largest known structures in the cosmos. Galaxy superclusters, stretching hundreds of millions of light-years, align along massive filaments of dark matter. Even larger formations, sometimes called walls, such as the Sloan Great Wall, reveal a cosmic architecture shaped by this invisible substance. Gravity from dark matter molds the large-scale arrangement of galaxies, dictating patterns that echo across billions of light-years. Theoretical models continue to expand the imagination. Some propose that dark matter might interact weakly with itself, forming halos and substructures within galactic cores. Others suggest it could be part of a more complex dark sector, with particles and forces entirely unknown to normal physics. The possibility that a hidden universe of interactions exists, invisible yet omnipresent, challenges our understanding and inspires speculation. Could there be entire dark galaxies, composed entirely of dark matter, moving silently through space, unseen by all telescopes? Even as scientists probe these mysteries, dark matter invites philosophical reflection. We exist in a universe where the majority of mass is invisible, yet its influence is omnipresent. The stars we see, the planets we inhabit, the galaxies we explore, all are guided by a substance we cannot touch or see. This reality reframes our perception of the cosmos, revealing that the luminous universe is merely the tip of a vast hidden iceberg. As we move through this section of the universe, the presence of dark matter becomes more than an abstract concept. It is a profound truth of cosmic architecture. It shapes the formation of galaxies, the distribution of clusters, and the evolution of cosmic filaments. It dictates motion on galactic scales, sculpts the cosmic web, and anchors structures across billions of light years. Dark matter is the invisible hand, the silent scaffolding that allows the luminous universe to exist as we perceive it. In contemplating dark matter, we confront the limits of perception and the power of inference. Though unseen, its presence is tangible through the motions of stars, the warping of light, and the growth of cosmic structures. It reminds us that reality extends beyond what can be seen, and that the universe is richer, stranger, and more intricate than human senses alone can detect. Thus, dark matter is both mystery and necessity, shaping the cosmos while eluding direct detection. It is the hidden framework, the scaffolding upon which all visible structures rest, guiding the evolution of galaxies and the universe itself. As we continue to explore, map, and theorize, we edge closer to understanding this unseen force. Yet it remains a reminder that even in a universe so vast and luminous, the greatest truths may lie in the shadows. As we navigate the cosmos, we discover that gravity, while powerful, is not the sole sculptor of cosmic fate. In the late 20th century, astronomers made a startling discovery that changed our understanding of the universe. It is not just expanding, it is accelerating. Galaxies are moving away from one another faster and faster, and the force driving this acceleration is one of the deepest mysteries of modern science. This unseen phenomenon is called dark energy, a pervasive energy field that dominates the universe, pushing space itself to stretch and expand at ever-increasing rates. Dark energy constitutes roughly 68–70% of the total energy density of the universe, far surpassing ordinary matter and dark matter combined. Unlike dark matter, which attracts through gravity, dark energy repels. It acts in opposition to the gravitational pull of matter, creating a tension in the fabric of space. This tension stretches space on the grandest scales, affecting entire galaxies and clusters, and driving the cosmic acceleration that has reshaped our understanding of the cosmos. The discovery of dark energy came from observations of distant supernovae in the 1990s. Astronomers noticed that these exploding stars were dimmer than expected, implying that they were farther away than calculations based solely on visible matter suggested. The expansion of the universe was accelerating, a finding that contradicted the long-standing assumption that gravity would slow expansion over time. This revelation stunned the scientific community, forcing a fundamental reassessment of cosmic dynamics. Unlike matter, which clumps under gravity, dark energy is uniform and pervasive. It does not collapse into stars or galaxies. It does not interact with light. Instead, it fills space itself, producing a negative pressure that drives expansion. In cosmological terms, it behaves like a property of space, an inherent energy of the vacuum. This concept aligns with Albert Einstein's cosmological constant, an idea he originally introduced to achieve a static universe, later discarded, but now resurrected as a leading explanation for dark energy. The accelerating expansion has profound implications for the universe's future. As galaxies move farther apart, light from distant stars and galaxies will become increasingly redshifted, stretched to longer wavelengths until they fade beyond detection. The universe could become a dark, cold, an isolated expanse, with galaxies drifting apart like islands in an ever-expanding cosmic ocean. In this scenario, distant galaxies will disappear from view, leaving only the local group of galaxies bound together by gravity, including our Milky Way, Andromeda, and their companions. Dark energy also influences the shape and geometry of the universe. Observations of the cosmic microwave background, the afterglow of the Big Bang, indicate that space is remarkably flat on large scales. For the universe to maintain this flatness, the total energy density must reach a critical value, a balance achieved only when dark energy is included in the cosmic equation. Without it, the universe's geometry would be different, either curving inward toward collapse or outward toward an open, ever-expanding void. Despite its overwhelming influence, dark energy remains largely enigmatic. Its origin is unknown. Some theories suggest it is a property of empty space itself, a quantum vacuum energy arising from the fundamental fluctuations of fields. Others propose dynamic fields, such as quintessence, which vary in intensity over space and time. More radical ideas consider modifications to general relativity, suggesting that our understanding of gravity may need adjustment on cosmic scales. Each theory offers glimpses into the profound nature of this invisible force, yet none fully explain its origin or magnitude. Dark energy is also intimately linked with the fate of the universe, a concept that has fascinated and troubled scientists and philosophers alike. If dark energy remains constant, the universe will continue expanding indefinitely, becoming colder and emptier over trillions of years. Stars will exhaust their fuel, galaxies will age into ghostly remnants, and black holes may dominate the distant cosmos, slowly evaporating through Hawking radiation. In this big freeze scenario, the universe becomes a vast, dark, and silent expanse, with energy too diffuse to sustain new structures. Alternatively, if dark energy strengthens over time, it could lead to a more dramatic fate known as the Big Rip. In this scenario, the repulsive force of dark energy grows so intense that it overcomes all gravitational and electromagnetic forces. Galaxies, stars, planets, and even atoms themselves could be torn apart as space stretches faster than light can traverse it. The universe would end in a singular, catastrophic dissolution, a stark contrast to the silent fade of the Big Freeze. The study of dark energy also challenges our philosophical understanding of existence. We inhabit a universe where the majority of its energy is invisible and mysterious, shaping everything from the largest clusters of galaxies to the motion of our own solar system. The accelerating expansion emphasizes the impermanence of cosmic structures, reminding us that even galaxies and clusters are transient formations in a vast, dynamic cosmos. The universe is not static or eternal. It is an evolving, breathing entity, governed by forces we barely comprehend. Observationally, scientists continue to probe dark energy through a variety of methods. Surveys of supernovae, large-scale galaxy clustering, and gravitational lensing provide clues about its properties and evolution. Space-based observatories, such as the Euclid mission and the upcoming Nancy Grace Roman Space Telescope, aim to map the expansion history of the universe with unprecedented precision. By measuring the subtle distortions of cosmic structures over time, astronomers hope to reveal whether dark energy is constant or dynamic, a fundamental property of space or a sign of new physics. Dark energy also interacts with dark matter in shaping the universe. While dark matter forms the cosmic scaffolding, drawing galaxies into clusters and filaments, dark energy stretches the fabric of space between these structures. Together, these unseen forces define the cosmic dance. One pulls, the other pushes, creating a balance that governs the growth and distribution of galaxies. Without dark energy, the universe might have collapsed or formed differently. Without dark matter, galaxies would not have formed at all. Their interplay highlights the intricate complexity of the cosmos, where the visible universe is only a minor player in a drama dominated by invisible actors. On smaller scales, dark energy has minimal effect. Gravity dominates in galaxies and clusters. Yet on the largest scales, its influence is undeniable. The accelerated expansion reshapes the observable universe, stretching space itself and altering our perception of distance and time. Light from distant galaxies becomes redshifted, shifting to longer wavelengths, a cosmic Doppler effect that encodes the history of expansion. By studying this redshift, astronomers can reconstruct the expansion rate of the universe over billions of years, revealing the imprint of dark energy on cosmic history. The discovery of dark energy represents one of the greatest scientific revolutions of the modern era. It overturns assumptions about cosmic deceleration and challenges our understanding of gravity, energy, and the ultimate fate of the universe. Dark energy is both a frontier and a mystery, a force that dominates the cosmos, yet remains largely beyond comprehension. Its presence reshapes space, time, and the distribution of matter, creating a universe that is dynamic, evolving, and in many ways, stranger than fiction. In contemplating dark energy, we confront the limits of human understanding. We observe galaxies receding ever faster, a silent expansion driven by an invisible hand. We infer its existence through subtle distortions in light and motion, yet we cannot touch, see, or directly measure it. Dark energy teaches humility, revealing that the cosmos is governed by forces far beyond everyday experience, forces that challenge intuition and demand imagination. Ultimately, dark energy frames our view of the universe in both time and space. It defines the cosmic horizon, setting the limits of what we can observe and shaping the trajectory of all galaxies. It determines the universe's geometry and expansion, dictates the future of cosmic structures, and highlights the profound mystery that the majority of the universe is dominated by an unseen, enigmatic energy. As we continue our journey through the cosmos, we must grapple with this invisible force, recognizing that the universe's ultimate destiny lies in its grasp. Dark energy is the silent architect of cosmic expansion, the driver of acceleration, and the force that will define the universe for trillions of years. It is the hidden dynamo stretching space itself, a reminder that even in a universe teeming with stars and galaxies, the most powerful forces are often unseen, operating in shadows that challenge our perception and expand the horizons of imagination. As we drift farther into the vastness of space, we encounter the ultimate boundary of human observation, the cosmic horizon. The universe, despite its staggering scale, is not equally visible in all directions. The light from distant galaxies takes billions of years to reach us, and the expansion of space stretches that light to longer wavelengths, dimming and reddening it along the way. This creates a natural limit, the observable universe, a sphere centered around Earth, beyond which we cannot yet see. What lies beyond this cosmic horizon may be as vast, strange, and intricate as the cosmos we can observe, but it remains inaccessible, hidden by the finite speed of light and the relentless expansion of space. The observable universe spans an estimated 93 billion light-years in diameter, an inconceivable distance that challenges even the most imaginative mind. Each point within this sphere represents light that has traveled to us across eons, carrying with it the story of the universe's past. When we look at a galaxy 1 billion light-years away, we are seeing it as it existed a billion years ago. A snapshot of its history, frozen in the beams of light, reaching our telescopes today. The farther we peer, the further back in time we see, gradually approaching the origin of the cosmos itself, the fiery birth of the Big Bang. Yet the observable universe is only a fraction of the total universe. Beyond the cosmic horizon, light has not had time to reach us. And because space itself expands, some regions may forever remain beyond our perception. This leads to a staggering conclusion. Much of the universe exists outside our observational grasp, beyond the limits of even the most powerful telescopes. There could be galaxies, stars, and structures unimaginably distant, each following the same laws of physics we know, yet forever separated from us by the inexorable expansion of space. The cosmic horizon is not a fixed boundary, but a dynamic one. As time progresses, light from more distant regions slowly reaches us, expanding the observable universe. In billions of years, we may witness galaxies now beyond our horizon, their light finally arriving after traversing unimaginable distances. However, due to the accelerating expansion driven by dark energy, some regions will never enter the observable universe. Galaxies receding faster than the speed of light will remain forever hidden, unreachable, and invisible, isolated in a vast cosmic ocean. Understanding the observable universe requires grappling with the concept of commoving distance, a measure of distance that accounts for the expansion of space itself. A galaxy observed today at 10 billion light-years away may have been much closer when it emitted the light we now see, yet the expansion of space over cosmic time has stretched that distance far beyond what simple intuition suggests. The interplay of light, time, and expanding space defines the contours of what we can observe, shaping our cosmic horizon and influencing our perception of the universe's scale. Within the observable universe, matter is not distributed uniformly. Galaxies cluster into groups and filaments, separated by vast voids where few stars exist. These structures form a cosmic web, a vast lattice stretching across billions of light-years. The cosmic web is shaped by the interplay of gravity and dark matter, with dark energy subtly influencing the spacing and motion of clusters. When we gaze into the night sky, the stars we see are but a fraction of the total galactic population, dwarfed by the sprawling network of galaxies beyond naked eye perception. Observing the universe also allows us to glimpse its history. The cosmic microwave background, the faint afterglow of the Big Bang, lies at the edge of the observable universe, approximately 13.8 billion years away in time. This radiation provides a snapshot of the cosmos when it was only 380,000 years old, a baby universe filled with a hot, dense plasma. By studying its subtle variations in temperature and density, astronomers reconstruct the initial conditions that gave rise to galaxies, stars, and planets, tracing the evolution of the cosmos from its earliest moments to the present. The observable universe is also defined by light itself. Light travels at a finite speed, creating a time delay that acts as a natural barrier. No matter how powerful a telescope, we cannot observe regions whose light has not yet reached us. Moreover, as the universe expands, the wavelengths of light from distant galaxies are stretched, eventually moving into the infrared or radio spectrum, making detection increasingly difficult. Even if technology improves, some regions may remain forever beyond our observational capabilities due to the accelerating expansion of space. Despite these limitations, astronomers have devised ingenious methods to probe the farthest reaches of the observable universe. Telescopes sensitive to different wavelengths, radio, infrared, optical, ultraviolet, X-ray, and gamma-ray, allow us to study distant galaxies and phenomena invisible to the naked eye. Gravitational lensing, where massive objects bend light from more distant sources, acts as a natural telescope, magnifying galaxies billions of light-years away. These techniques provide glimpses into the universe's past, revealing structures and events otherwise hidden, and pushing the boundaries of what we can see ever farther. The observable universe is also a story of cosmic perspective. From Earth, it appears as a sphere centered on our location, yet this is not a special position. Every observer in the universe, anywhere in a distant galaxy, would perceive a similar sphere, their own observable universe centered on their position. This reflects the cosmological principle. The universe is homogeneous and isotropic on large scales, with no preferred location or direction. Our cosmic horizon is personal yet universal, a reminder that all observers share the same laws of physics, even as each perceives their own bounded view of space and time. In contemplating the cosmic horizon, we confront the limits of human perception and imagination. We realize that what we see is a fraction of reality, that the universe extends far beyond the reach of light and observation. This perspective is humbling and exhilarating, reminding us that the cosmos is far larger and more complex than our senses alone can perceive. The observable universe is a stage for countless cosmic dramas, from the birth of stars to the collision of galaxies, yet beyond its edge lies an untold expanse of potential, a universe of mysteries waiting beyond our reach. The cosmic horizon also emphasizes the importance of time in understanding the universe. Observing distant galaxies is equivalent to looking back in time, witnessing events billions of years in the past. Each photon arriving at Earth carries a story of cosmic evolution, allowing us to reconstruct the life cycles of galaxies, the formation of stars, and the emergence of planetary systems. Time and distance are inseparable in this grand cosmic narrative, defining the boundaries of observation and shaping our understanding of the universe's scale. Moreover, the cosmic horizon is intimately linked with dark energy and the universe's expansion. As dark energy drives accelerated expansion, distant galaxies recede ever faster, pushing some regions beyond the reach of observation. The observable universe, while vast, is ultimately finite, bounded by the speed of light and the dynamics of cosmic expansion. Beyond the horizon lies an unobservable realm, possibly infinite, stretching into realms we can never witness. This interplay of physics, light, and time defines the limits of human knowledge, marking the edge of the universe we can explore with observation alone. In essence, the observable universe is both a window and a barrier. It offers an unparalleled view of cosmic history, revealing galaxies, clusters, and the relic radiation of the Big Bang. Yet it also reminds us of our limitations, highlighting that the universe's true scale extends far beyond what we can see. Every discovery within this horizon, from the nearest stars to the faintest galaxies, is a testament to human curiosity and ingenuity, a small beacon illuminating the vastness of a cosmos that stretches beyond comprehension. The cosmic horizon inspires both wonder and humility. It challenges us to imagine realms we cannot see, to conceive of distances that defy intuition, and to appreciate the fleeting nature of observation in a universe in constant motion. The observable universe, immense and awe-inspiring, is a testament to the interplay of light, space, and time, offering a glimpse of a cosmos that is vast, dynamic, and infinitely mysterious. In the end, the cosmic horizon reminds us that while we may never reach the edge of the universe, our curiosity allows us to glimpse its depths. It teaches that observation is a journey through both space and time, connecting the present with billions of years of cosmic history. Every photon captured, every distant galaxy observed, brings us closer to understanding our place in the universe, even as the horizon stretches ever outward, inviting us to imagine the infinite beyond. As we peer beyond the edge of the observable universe, the mind inevitably drifts toward possibilities that stretch the imagination. What if our universe is not alone? What if the cosmos we inhabit is but one of countless others, each with its own laws of physics, its own galaxies, and perhaps its own forms of life? This is the realm of the multiverse, a concept that challenges everything we think we know about reality, suggesting that the universe we see, the galaxies, stars, and voids stretching across billions of light years, may be only one bubble in an immense cosmic foam of countless universes. The idea of a multiverse arises from several lines of theoretical reasoning. One of the most influential comes from inflationary cosmology. According to this theory, the universe underwent a period of exponential expansion in the first fractions of a second after the Big Bang. Quantum fluctuations during inflation could have caused pockets of space to expand differently, creating separate, self-contained universes. In this model, each bubble universe could have its own distinct laws of physics, varying constants, and structures unlike anything we can observe. Our universe might be a single bubble in an infinite sea of cosmic foam, each bubble a universe unto itself. Another route to the multiverse comes from string theory, a mathematical framework that attempts to unify all forces of nature. String theory suggests that reality may have many dimensions beyond the familiar three of space and one of time. In this landscape, different regions of space-time could settle into different configurations, giving rise to universes with varied physical properties. One universe might allow stars and planets to form as ours does, while another might be dominated by strange forms of matter, with no familiar elements at all. The multiverse becomes a mathematical inevitability, a consequence of the vast landscape of possible physical laws encoded in the fabric of reality. Parallel universes are not limited to distant, separate bubbles. Some theories suggest they might exist alongside our own, overlapping yet invisible. The concept of a quantum multiverse emerges from the many worlds interpretation of quantum mechanics. Every time a quantum event occurs, every time a particle chooses one path or another, a new branch of reality is created, forming a parallel universe where the alternative outcome plays out. In this view, there are countless versions of our universe, each slightly different, containing alternate histories, choices, and possibilities. Somewhere, in a universe indistinguishable from ours, perhaps a version of you has taken a different path, living a life shaped by a single different decision. The multiverse also emerges from the study of black holes and cosmology. Some theories propose that black holes may seed new universes, with their singularities forming the cause of entirely separate realms. Matter collapsing into a black hole in our universe could trigger a Big Bang-like event in another, creating a cosmos entirely disconnected from ours, with its own timeline and physics. In this scenario, every black hole becomes a potential universe incubator, endlessly multiplying the possibilities of existence. Though the multiverse remains speculative, it raises profound philosophical and scientific questions. If countless universes exist, each with varying physical laws, why do we find ourselves in one capable of supporting life? This is known as the anthropic principle. Only universes with conditions suitable for life will host observers capable of contemplating them. The existence of life in this context is not miraculous, but a natural consequence of cosmic selection among an immense variety of universes. Our universe may be one of many, but it is special simply because it allows beings to ponder its vastness. Imagining the multiverse stretches our intuition in every direction. Time, space, and causality may operate differently in other universes. In some, the speed of light might be slower or faster, stars might never form, or atoms might behave in ways that defy our comprehension. The scale of these parallel realms is inconceivable, potentially infinite, extending in directions that cannot be mapped within our universe. We are left with the humbling realization that the cosmos may be far larger and more complex than even the grandest astronomical observations can reveal. Evidence for a multiverse remains indirect. Cosmic microwave background radiation, the faint afterglow of the Big Bang, carries subtle anomalies that some theorists interpret as possible signs of collisions with other universes. Large-scale surveys of galaxy distribution and fundamental constants suggest a fine-tuning that may hint at a broader landscape of realities. Yet, direct observation of parallel universes remains beyond current technological reach, raising the question of whether the multiverse is scientifically testable or forever resides in the domain of theoretical speculation. The multiverse has implications that stretch beyond physics into philosophy and imagination. If countless realities exist, every possibility, every outcome may play out somewhere. This reshapes our understanding of fate, choice, and existence itself. In a multiverse, the improbable becomes inevitable. Galaxies may form in patterns alien to ours, planets may harbor forms of life unimaginable, and civilizations may rise and fall in ways we cannot predict. Our reality becomes one story among countless others, a narrative thread woven into an infinitely larger tapestry. Some thinkers explore the multiverse through the lens of consciousness. Could minds somehow traverse or perceive parallel realities? While purely speculative, these ideas provoke reflection on the nature of awareness and existence. Are we confined to one thread of reality, or is consciousness more fluid, capable of experiencing multiple outcomes across the vast multiverse? These questions lie at the intersection of physics, philosophy, and metaphysics, inviting contemplation of reality's ultimate boundaries. The idea of a multiverse also offers a way to confront cosmic loneliness. In an infinite collection of universes, life may arise elsewhere, perhaps in forms we cannot recognize. Civilizations could emerge in entirely different cosmic settings, governed by unfamiliar physics. While contact may be impossible, the multiverse suggests that existence is not unique to our universe, but part of a broader, possibly infinite ensemble of realities. The loneliness of our cosmic island may be mitigated by the awareness of countless others, each a unique experiment in the possibilities of existence. Mathematically, the multiverse challenges conventional notions of probability and infinity. If universes are infinite in number, every conceivable event occurs somewhere, an unsettling concept that stretches logic to its limits. Every choice, every fluctuation, every quantum event gives rise to new realities, creating an unending proliferation of worlds. Our imagination strains to hold such vastness, yet physics suggests that the multiverse may be as real as the stars we see or the galaxies we observe. Despite the grandeur of multiverse theories, they underscore the limits of human perception. Our instruments measure only the universe accessible to observation, constrained by light and time. Beyond this boundary lies speculation, mathematics, and theory. Yet even within these constraints, the multiverse invites awe, revealing that our universe, already vast beyond comprehension, may be only one of an infinite ensemble of realities, each with its own grandeur, mystery, and possibility. Ultimately, the multiverse reshapes our cosmic perspective. The universe we know, the galaxies, stars, and planets visible through telescopes, is only part of a potentially infinite mosaic of existence. Each parallel realm or bubble universe expands the scope of imagination, suggesting that reality itself is far richer and more complex than our observations allow. The multiverse becomes not merely a scientific hypothesis, but a philosophical lens through which we grasp the scale of existence, the nature of possibility, and the endless potential of the cosmos. In contemplating the multiverse, we confront both the limits and the potential of human understanding. The universe we inhabit is vast, beautiful, and enigmatic, but it may be just a fragment of a larger reality. Beyond our cosmic horizon, in realms we may never see, exist universes governed by different laws, brimming with possibilities. To imagine them is to expand the boundaries of thought, to journey into infinity without leaving the confines of our own universe. The multiverse reminds us that the universe is not a static stage, but an ever-expanding tapestry of possibilities. It challenges our assumptions about uniqueness, reality, and existence itself, suggesting that what we see is only a small window into a vast, multifaceted cosmos. As we contemplate parallel worlds, infinite bubbles, and countless timelines, we realize that the universe, or rather, the multiverse, is beyond measure, beyond imagination, and endlessly mysterious. As we continue our journey across the unimaginable expanse of the cosmos, we encounter a mystery that lurks invisibly, quietly orchestrating the movements of galaxies and the evolution of the universe itself. It is a mystery that neither glows nor absorbs light, a substance and force that reveals itself only through the gravitational and dynamic effects on visible matter. These are the enigmas of dark matter and dark energy, hidden yet colossal forces that together make up roughly 95% of the universe, an astonishing realization that leaves humanity peering at only a tiny fraction of all that exists. The concept of dark matter first emerged in the 1930s, when the Swiss astronomer Fritz Zwicky observed that galaxies in the Coma cluster were moving far faster than their visible mass could account for. Gravity from the stars and gas alone was insufficient to hold these galaxies together. Zwicky proposed the presence of unseen mass, an invisible substance exerting gravitational pull, coining the term dunkel Materie, or dark matter. Decades of observation have confirmed this mysterious presence. Galaxies rotate in ways that suggest far more mass exists than we can see. Cosmic structures form and cluster as if guided by an invisible scaffold. And the motions of galaxy clusters reveal gravitational influences that light alone cannot explain. Dark matter is not merely a curiosity, it is a cornerstone of cosmic architecture. Without it, galaxies might never have formed, stars might never have ignited, and planets and life might never have emerged. Yet despite its profound influence, dark matter remains invisible, detectable only through its gravitational effects. It does not emit, absorb, or reflect light, making it impervious to traditional astronomical observation. The hunt for its identity, whether it is composed of exotic particles, massive compact halo objects, or something more profound, continues to challenge physicists worldwide. In parallel, the universe presents another, even stranger puzzle: dark energy. In 1998, astronomers observing distant supernovae discovered that the universe is not merely expanding, its expansion is accelerating. Gravity alone should be slowing the expansion, yet something unseen is driving galaxies ever farther apart at increasing speeds. This mysterious force, dubbed dark energy, constitutes approximately 68% of the total energy density of the universe, dominating the cosmos on the largest scales. Unlike dark matter, which pulls through gravity, dark energy exerts a repulsive effect, a kind of anti-gravity that stretches the very fabric of space-time itself. The interplay of dark matter and dark energy defines the universe we inhabit. Dark matter acts as the scaffolding, guiding the formation of galaxies and cosmic filaments, while dark energy stretches the cosmic fabric, driving galaxies apart and shaping the ultimate fate of the cosmos. Together, they form a cosmic yin and yang, invisible forces that shape everything we observe, yet remain largely mysterious. The evidence for these hidden forces comes from multiple lines of observation. Cosmic microwave background radiation, the faint afterglow of the Big Bang, carries subtle patterns influenced by the distribution of dark matter. Observations of galaxy rotation curves reveal the gravitational pull of invisible mass. Large-scale surveys of the universe show cosmic filaments and voids that align with predictions of dark matter-driven structure formation. Meanwhile, precise measurements of distant supernova, galaxy clusters, and gravitational lensing demonstrate the accelerating expansion driven by dark energy. The universe, it seems, is a vast stage choreographed by forces beyond the reach of our senses. Yet despite these profound discoveries, dark matter and dark energy remain largely theoretical constructs. Numerous experiments aim to detect dark matter particles directly, using highly sensitive detectors buried deep underground, shielded from cosmic rays. The Large Hadron Collider and other particle accelerators seek to produce or identify these elusive particles, while space-based observatories scan for indirect signals, such as gamma rays from hypothetical dark matter annihilation. Dark energy, by contrast, remains even more enigmatic, its nature possibly tied to the cosmological constant proposed by Einstein, or to an unknown field permeating space-time. Some physicists suggest it may hint at a deeper modification of gravity itself, a radical shift in our understanding of physics. The existence of these hidden forces reshapes our cosmic perspective. What we see, the stars, planets, nebulae, and galaxies, is merely the visible tip of a vast, invisible iceberg. The ordinary matter we understand, the atoms that compose everything familiar, constitutes a mere 5% of the universe. The rest is governed by entities we cannot see or touch, yet whose influence is undeniable. It is humbling to realize that the grand, awe-inspiring galaxies visible through telescopes are but minor participants in a drama dominated by dark matter and dark energy. Understanding these hidden forces also reshapes our perception of the universe's ultimate destiny. If dark energy continues to dominate, galaxies will drift ever farther apart, stars will burn out, and the cosmos may enter a state of cold, dark isolation, known as the heat death. Dark matter, meanwhile, provides the glue that allows galaxies to persist and cluster, giving the universe structure amid the accelerating expansion. These unseen forces dictate not only the present configuration of the cosmos, but also its long-term evolution, guiding the universe toward a fate we are only beginning to comprehend. The search for understanding has inspired humanity to explore both theoretically and technologically. Advanced telescopes, such as the James Webb Space Telescope, probe the cosmos at infrared wavelengths, seeking clues about the distribution of dark matter. Gravitational lensing, where light from distant galaxies bends around invisible mass, provides a cosmic map of dark matter's structure. Meanwhile, experiments like the Dark Energy Survey aim to chart the acceleration of cosmic expansion with unprecedented precision. Each observation, each data point, offers a glimpse into the invisible forces shaping the universe. Yet even as we probe deeper, dark matter and dark energy remind us of the limits of knowledge. They are a testament to the vastness of what we do not yet understand, a challenge to human curiosity and ingenuity. They reveal that the universe is not merely a collection of visible stars and galaxies, but a complex, layered reality, governed by forces that defy direct perception. In contemplating them, we confront the profound mystery that the cosmos is far richer and stranger than our senses allow us to perceive. Philosophically, these hidden forces invite reflection on our place in the universe. Humanity has long measured existence by what can be seen, touched, and comprehended. Yet most of the cosmos is invisible, hidden in plain sight, shaping reality in ways we cannot directly perceive. The stars and galaxies we observe are illuminated not just by their own light, but by the gravitational and dynamic influence of dark matter, their movements and clustering dictated by unseen laws. The accelerating expansion, driven by dark energy, reminds us that the cosmos is alive with motion and evolution beyond comprehension. Dark matter and dark energy also inspire imagination and storytelling. They are the unseen architects of galaxies, the invisible engines propelling cosmic expansion, the silent sculptors of structure and fate. To gaze into the night sky, knowing that the light of distant stars is only a fraction of what exists, is to experience both wonder and humility. The universe is not static, but a dynamic, unfolding entity, governed by invisible hands that shape the cosmos in profound, mysterious ways. In the grand narrative of the cosmos, dark matter and dark energy are the hidden chapters that define the story. They remind us that the universe is not merely what we see, but a complex interplay of visible and invisible forces. Every galaxy, every star, every cosmic filament is part of a vast, intricate dance orchestrated by these hidden forces. To understand the universe fully, we must peer beyond light, beyond matter, beyond the familiar, into the invisible currents that guide reality itself. As we continue to chart the cosmos, the mystery of dark matter and dark energy invites both scientific inquiry and philosophical reflection. They challenge our perceptions, expand the boundaries of imagination, and underscore the profound truth that the universe is far more complex than our senses reveal. The stars and galaxies are only the beginning. The hidden forces behind them are the true masters of cosmic architecture, shaping existence on scales both vast and invisible. In contemplating these hidden forces, we grasp that the universe is an intricate web of visible and invisible threads, a tapestry woven from light and shadow, matter and energy, known and unknown. Dark matter and dark energy are not merely scientific puzzles. They are gateways to understanding the deepest structure of reality, a reminder that the universe is at once grand, mysterious, and far larger than we can ever fully perceive. As we drift further into the vastness of the universe, we encounter the concept of cosmic horizons, the ultimate limits imposed on our ability to observe and understand the cosmos. Just as a ship at sea disappears over the horizon, so too do distant regions of the universe slip beyond our vision, unreachable and forever hidden from direct observation. These horizons are not merely philosophical, they are dictated by the laws of physics, the finite speed of light, and the ongoing expansion of space-time itself. The first horizon we encounter is the observable universe, the region of space from which light has had time to reach us since the beginning of the cosmos. Light, though fast at nearly 300,000 kilometers per second, is not instantaneous. The universe is about 13.8 billion years old, so photons emitted from regions beyond a certain distance have not yet had time to arrive at Earth. This forms a spherical boundary around us, a cosmic bubble of visibility. Beyond it lies the unobservable universe, a realm that may exist, but remains forever beyond our current reach. Interestingly, due to the expansion of space, the observable universe extends much farther than 13.8 billion light-years. Galaxies we see today were much closer when the light left them, but as the universe expanded over billions of years, those galaxies are now over 46 billion light-years away. This introduces the concept of co-moving distance, a measure that accounts for the expansion of the universe over time. The observable universe is, therefore, a snapshot of a cosmic past, a window into the history of space, not merely a map of present locations. Beyond this horizon lies an even deeper limit, the cosmic event horizon. This boundary is determined by the accelerating expansion of the universe, driven by dark energy. As space stretches, distant galaxies recede faster and faster, eventually moving away from us at speeds exceeding the speed of light relative to our frame of reference. Once a galaxy crosses this cosmic event horizon, its light will never reach us, no matter how long we wait. In practical terms, this means that a vast portion of the universe is destined to remain forever hidden, slipping silently into isolation as expansion outpaces our observational reach. The cosmic horizons are not mere abstract concepts. They shape the very nature of the universe we can study. Astronomy and cosmology are intrinsically limited by what light and other signals can reach us. We construct our models based on photons, neutrinos, gravitational waves, and cosmic rays, each carrying fragments of information across unimaginable distances. But no signal from beyond the event horizon will ever arrive. There are corners of the cosmos where galaxies and clusters exist, evolving and interacting, yet entirely invisible to every telescope we could ever build. The universe, therefore, is much larger than the patch illuminated for our observation, a humbling reminder of our limited perspective. Even within the observable universe, our view is shaped by look-back time, the fact that we are seeing distant objects as they were in the past. A galaxy a billion light-years away appears not as it is now, but as it was a billion years ago. The farther we peer, the younger the universe appears. Observing the cosmic microwave background, for example, is like seeing the universe as it was 380,000 years after the Big Bang, a faint afterglow that tells the story of the universe's infancy. We are, in essence, looking backward through time, observing history unfolding across the fabric of space-time. The concept of horizons also challenges our understanding of cosmic uniformity. The universe appears remarkably homogeneous and isotropic on large scales, meaning it looks roughly the same in every direction. Yet regions separated by vast distances may never have exchanged information due to the limits imposed by horizons. This leads to profound questions about cosmic inflation, the rapid expansion of the universe in its earliest moments. Inflation theory proposes that the observable universe originated from a tiny, causally connected region, expanded exponentially, and became large enough to encompass all we see today. Horizons, therefore, are not just limits, they are clues to the universe's earliest history and the processes that shaped its large-scale structure. Gravitational waves, ripples in space-time caused by massive cosmic events, offer another avenue for probing horizons. Unlike light, gravitational waves can traverse regions of space that may be opaque to electromagnetic radiation, carrying information from otherwise inaccessible realms. Observations of these waves provide insights into black hole mergers, neutron star collisions, and perhaps even the early universe itself. Yet even these signals are bound by cosmic horizons. There is a limit to how far back we can detect these disturbances. The universe's expansion and finite age ensure that certain events remain forever beyond observational reach. Cosmic horizons also shape the future of exploration and observation. As dark energy drives accelerating expansion, more and more galaxies will recede beyond the event horizon. In billions of years, the night sky, as seen from the Milky Way or any galaxy, will appear almost empty, with only local galaxies remaining visible. The universe will feel lonelier and smaller, not because it is shrinking, but because the expansion isolates distant regions beyond our observational capabilities. Future civilizations may infer less about the broader cosmos, unable to see the vast structures and cosmic microwave background that inform our understanding today. The interplay of cosmic horizons and the speed of light also informs our understanding of causality and the structure of space-time. Events separated by distances beyond the event horizon cannot influence each other, establishing a fundamental limit on communication and interaction. This limitation shapes cosmic evolution and the ultimate fate of structures in the universe. Clusters of galaxies may continue to evolve independently, yet remain forever isolated from one another, their stories unobservable to distant civilizations. The universe, it seems, is partitioned into realms defined not just by distance, but by the flow of information and the expansion of space itself. Horizons also challenge philosophical and existential perspectives. The universe is vast beyond comprehension, yet the portion we can see is finite. A luminous bubble surrounded by mystery, our knowledge is constrained by the physics of light and expansion, and the regions beyond the observable universe may harbor structures, galaxies, and even civilizations we will never witness. There is a poetic tension between the vastness of the universe and the limits imposed on our perception. We are explorers on a small stage, peering outward, aware of the immeasurable, yet bound by the boundaries of cosmic visibility. Even as telescopes, detectors, and space observatories improve, cosmic horizons impose a fundamental limit. We can see farther, map more galaxies, detect fainter signals, and uncover deeper layers of cosmic history. But there will always be regions, always unobservable, forever beyond our reach. These limits are not failures of technology, they are intrinsic to the structure of space-time itself. In contemplating them, we confront the universe's vastness, not just in space, but in principle, acknowledging that part of reality will always remain hidden, whispering its secrets beyond the horizon. Horizons also guide the design of future observational campaigns. Scientists carefully plan surveys, satellite missions, and ground-based telescopes to maximize information within the observable universe, seeking to infer properties of regions beyond the visible limit. By studying the cosmic microwave background, galaxy clustering, and gravitational lensing, researchers attempt to reconstruct the larger cosmos and test theories about its global structure. Even indirect evidence allows us to glimpse theoretically the universe beyond our observational reach, offering tantalizing hints of the unobservable. In sum, cosmic horizons are both constraints and guides. They define the boundaries of what we can see, yet inspire the imagination to reach beyond. They shape our understanding of the universe, from its earliest moments to its ultimate destiny, and challenge us to reconcile what is known with what may forever remain unknown. The universe, though incomprehensibly vast, presents a stage where light and time impose limits on knowledge, yet offer windows of insight into the grand cosmic story. The journey through cosmic horizons teaches us humility, patience, and wonder. It reminds us that while we can chart galaxies, measure the cosmic microwave background, and study gravitational waves, the universe extends far beyond the edge of perception. Every observation is a window into history, every measurement a glimpse of the invisible, and every horizon a boundary inviting curiosity. The cosmos is not merely a collection of objects. It is a dynamic, expanding, and partially hidden reality, where the limits of observation define both our understanding and the mystery that drives exploration. As we ponder the limits imposed by cosmic horizons, we realize that the universe is far larger than our instruments can measure, far more complex than our minds can fully grasp. It is a realm of light and shadow, knowledge and mystery, proximity and distance. The observable universe is a luminous island in a dark, unmeasured ocean of space, and the horizons that define it are as profound as the cosmos itself. To explore the universe is to navigate these boundaries, to witness history in transit, and to wonder at the vast, uncharted territories that lie beyond. As we advance in our cosmic journey, another profound question emerges. What is the shape of the universe? Beyond the sheer size, beyond the cosmic horizons and unobservable regions, the very geometry of space itself becomes a subject of exploration. The universe is not merely an expanse of galaxies and voids. It has a form, a structure at the largest scales, dictated by gravity, energy, and the underlying laws of physics. Understanding this geometry helps us comprehend not only how the cosmos stretches outward, but also how it evolves over time, how it began, and how it may end. The shape of the universe is tied to its curvature, which can be broadly categorized into three possibilities: flat, positively curved, or negatively curved. Imagine a two-dimensional analogy to simplify this concept. A flat surface, like a sheet of paper, extends infinitely without bending. A positively curved surface, like a sphere, loops back on itself. If you travel far enough in one direction, you eventually return to your starting point. A negatively curved surface, like a saddle, bends in a hyperbolic fashion, diverging as you extend outward. Our universe, though three-dimensional, follows similar principles of curvature, shaped by the distribution of matter and energy. The geometry of the universe is governed by Einstein's theory of general relativity, which connects mass, energy, and the curvature of space-time. Dense regions, such as galaxies and clusters, warp space-time locally, bending light and influencing motion. On the largest scales, the universe's overall curvature depends on its total energy density, including matter, radiation, and the mysterious dark energy. By measuring the curvature, cosmologists seek to determine whether the universe is flat, closed, or open, and this in turn informs predictions about its past, present, and future. Current observations suggest that the universe is remarkably flat, with only tiny deviations from perfect flatness. Measurements of the cosmic microwave background, CMB, the afterglow of the Big Bang, reveal patterns of temperature fluctuations that encode information about the universe's geometry. Instruments like the Planck satellite and the Wilkinson Microwave Anisotropy Probe, WMAP, have mapped the CMB with exquisite precision, showing that the universe's curvature is so close to zero that it is effectively flat on large scales. This flatness implies that parallel lines in space remain parallel, and the geometry obeys the familiar rules of Euclidean space. Yet the concept of a flat universe is nuanced. While space may be flat locally or on large scales, the universe is still dynamic and expanding. The distances between galaxies grow over time, stretching the fabric of space itself. This expansion is uniform on cosmic scales, meaning that, on average, the universe does not favor one direction over another. Observations of distant supernovae and the distribution of galaxy clusters confirm that this expansion is accelerating, driven by dark energy, further influencing the universe's geometry. The flatness we observe today is the result of delicate cosmic balancing acts over billions of years. If the universe were positively curved, it would resemble a three-dimensional sphere. In such a universe, traveling far enough in one direction would eventually bring you back to your starting point, a concept both dizzying and profoundly humbling. A closed universe has a finite volume, though without an edge in the conventional sense. Light traveling along curved paths would eventually intersect, producing multiple images of the same galaxy from different angles. Positively curved universes are associated with eventual contraction or a big crunch if dark energy were absent or insufficient to drive eternal expansion. While our observations favor flatness, the possibility of a slight positive curvature is still considered, because even tiny deviations can profoundly impact cosmological models. Conversely, a negatively curved universe resembles a saddle, expanding outward infinitely and diverging as one moves farther from any point. Such a universe would have infinite volume and unique geometric properties. Triangles drawn in space would have angles summing to less than 180 degrees, and parallel lines would eventually diverge. Open universes expand forever, cooling and diluting matter over time. This type of geometry, though not favored by current observations, is a valid solution to Einstein's equations and remains an intriguing theoretical possibility, particularly in multiverse scenarios or models of early inflation. One fascinating aspect of cosmic geometry is its connection to topology, the study of the universe's global shape. Even a flat universe could be finite if space has a complex topology, such as a three-dimensional torus, where traveling far enough in one direction could theoretically bring you back to the starting point. Detecting such a topology is challenging, but cosmologists search for repeating patterns in the cosmic microwave background that might hint at a finite yet unbounded cosmos. If such patterns exist, they would imply that our universe is far stranger than intuition suggests, a cosmic labyrinth wrapped in the fabric of space-time. Geometry also influences the cosmic fate. A flat universe with dark energy, as current data suggests, will expand forever, growing colder, emptier, and more isolated over trillions of years. Galaxies will drift apart beyond the event horizon. Cosmic horizons will retreat, and observers in distant epochs will see only the remnants of their local group. A positively curved universe could, under certain conditions, reverse its expansion and collapse, while a negatively curved universe will expand endlessly. Geometry, therefore, is not merely a static property, it shapes the destiny of the cosmos itself. The shape of the universe also affects the propagation of light and the observation of distant objects. Gravitational lensing, the bending of light around massive objects, allows astronomers to map dark matter and probe the distribution of mass on large scales. The curvature of space influences lensing patterns, as well as the angular sizes of distant galaxies and the spacing of fluctuations in the cosmic microwave background. By studying these subtle distortions, cosmologists infer the large-scale geometry and gain insight into the universe's overall structure. Every photon that reaches us carries the imprint of space-time geometry, a whisper of the universe's vast, curved expanse. Even more subtly, the geometry of space affects cosmic distances and the measurement of expansion. Standard candles, like Type Ia supernovae, and standard rulers, like baryon acoustic oscillations, rely on geometric principles to estimate distances across billions of light years. These measurements confirm the flatness of the universe while revealing the accelerating expansion driven by dark energy. Geometry, energy content, and expansion history are intertwined, forming a cosmic web of cause and effect that governs the evolution of space, time, and matter. Philosophically, contemplating the universe's shape challenges human intuition. A finite but unbounded universe defies conventional notions of inside and outside, edge and center. Infinity and curvature exist simultaneously, stretching the imagination as much as the telescope does. Our minds, accustomed to everyday Euclidean space, struggle to fully grasp the elegance of a cosmos that can be flat, curved, finite, or infinite, yet consistently governed by precise mathematical laws. Geometry becomes both a scientific and existential lens, revealing the harmony and mystery woven into the cosmos. The study of cosmic geometry also connects to inflationary theory, the idea that the universe underwent exponential expansion in its first fractions of a second. Inflation predicts a universe so large that it appears flat on observable scales, even if it curves globally. Tiny quantum fluctuations during inflation seeded the galaxies and clusters we observe today, creating the cosmic web. The precise geometry we measure, flat within a fraction of a percent, is a striking confirmation of these early universe processes, showing how initial conditions shaped the universe's structure over billions of years. Finally, geometry underscores the unity of the cosmos. From the orbits of planets to the expansion of space itself, from local curvature around stars to the large-scale shape of the universe, geometry connects phenomena across scales. It informs the evolution of cosmic structures, the fate of galaxies, and the pathways of light across billions of years. By understanding the universe's shape, we gain a framework for interpreting observations, predicting cosmic evolution, and contemplating the ultimate destiny of space, time, and matter. In summary, the shape and geometry of the universe are central to comprehending its vastness, history, and fate. The universe appears remarkably flat, yet its global topology may hide complexities beyond our observational reach. Curvature and expansion govern the motion of galaxies, the propagation of light, and the evolution of cosmic structures. Geometry defines the very stage on which the cosmic drama unfolds, shaping our understanding of beginnings, present structures, and ultimate outcomes. It reminds us that space itself is dynamic, intricate, and profoundly interconnected with the matter and energy it contains. The universe, therefore, is not just vast. It has form, texture, and curvature. It is a cosmic tapestry, woven with the threads of geometry, expansion, and energy, stretching endlessly outward while subtly bending in ways that challenge intuition. To study its shape is to navigate the architecture of reality itself, to glimpse the rules that govern the cosmos on its grandest scales, and to appreciate the profound elegance of a universe both immense and intricately structured. As we reach the final chapter of this cosmic exploration, the question emerges with an almost philosophical weight. Does the universe have limits? We have traversed the vast stretches of space, measured the expansion, explored the furthest observable regions, and examined the shape and geometry of existence itself. But beyond these investigations lies an even more profound frontier, the ultimate boundaries of reality, where science meets the edge of imagination and questions linger that may never be fully answered. When we speak of the limits of the universe, we must first distinguish between the observable universe and the total universe. The observable universe is defined by the distance that light has traveled since the Big Bang, roughly 46.5 billion light-years in every direction. It forms a cosmic sphere around Earth, encompassing all galaxies, stars, and matter, whose signals have reached us in the 13.8 billion years since the universe began. Beyond this horizon, there are undoubtedly galaxies, clusters, and structures we cannot see, because their light has not yet had time to reach us. In essence, the observable universe is a bubble of perception, limited by the speed of light and the age of time itself. Yet the total universe may extend far beyond this horizon. It could be infinite, stretching endlessly in all directions, or it could be finite but unbounded, curving back upon itself in ways we cannot yet perceive. If it is infinite, then every possible configuration of matter, energy, and space exists somewhere, including regions nearly identical to our own. If it is finite, then there may be a cosmic edge, a boundary where space-time itself ends or folds back, creating a self-contained universe. Modern cosmology offers no definitive answer. The universe's ultimate size may forever remain beyond our reach, a humbling reminder of our observational limits. Time itself imposes further constraints. The universe is dynamic, continually expanding, with distant galaxies receding ever faster due to cosmic acceleration. Many regions that are currently visible will eventually slip beyond our cosmic horizon, becoming unreachable to future observers. The accelerated expansion, driven by dark energy, creates a scenario known as the cosmic event horizon. Beyond this horizon, no signals, not even light, can ever reach us. It is a sobering realization. The universe we can observe today is not the same universe that will be observable in the distant future. The cosmos is not only vast, it is gradually withdrawing from us. Beyond spatial and temporal limits, there are also physical limits dictated by the laws of physics. The speed of light establishes the ultimate cosmic speed limit, bounding how quickly information, matter, or energy can traverse space. The Planck scale defines the smallest meaningful intervals of time and distance, where quantum fluctuations dominate and classical concepts of space and time cease to apply. Similarly, black holes represent regions where gravitational collapse creates a boundary, the event horizon, beyond which nothing can escape. In these extreme environments, the very fabric of space-time reaches its ultimate limits, compressing reality into singularities that challenge our understanding of physics. Entropy introduces yet another type of limit. According to the second law of thermodynamics, the universe is steadily moving toward a state of maximum entropy, often called heat death. Over unimaginable timescales, stars will burn out, galaxies will dissipate, and black holes will evaporate through Hawking radiation. Matter will decay, energy will spread thin, and the universe will approach uniformity, a cold, dark, and empty expanse where the dynamics of stars, planets, and life are no longer possible. This sets a temporal horizon, the ultimate limit for structure and complexity in the cosmos, a profound reminder of the finite lifespan of all things. Even the quantum nature of reality imposes limits. Quantum mechanics reveals that uncertainty governs the smallest scales, meaning that absolute precision is unattainable. There is a fundamental limit to how much we can know about the position and momentum of particles, about energy fluctuations, and even about the initial conditions of the universe itself. At the Planck length and Planck time, space-time itself may be subject to quantum foam, where conventional notions of continuity and geometry break down. In these realms, the universe exhibits its ultimate intricacy and elusiveness, teasing the boundaries of human comprehension. Cosmologists also speculate about multiverse scenarios, which suggest that our universe may be just one of countless others, each with different physical constants, dimensions, or laws of physics. In such models, our observable universe is a small patch within a vast meta-universe, bounded not by spatial distance, but by the fundamental rules that govern its formation. The concept of ultimate limits becomes more abstract here. Our universe may have local boundaries, but in a multiverse context, the cosmos itself is far vaster, potentially infinite, and populated by a diversity of realities beyond our perception. Here, the limits of our universe are defined not by size but by accessibility and observation. Despite these boundaries, observable horizons, event horizons, thermodynamic limits, quantum uncertainties, and potential multiverse separations, human curiosity relentlessly presses forward. We develop telescopes that peer deeper into space, particle accelerators that probe the smallest scales, and mathematical frameworks that model phenomena beyond direct observation. Every discovery extends the frontier of what is knowable, revealing that even the universe's ultimate limits are dynamic. They shift as our understanding grows. The limits are not absolute. They are the interplay between physical laws and human ingenuity, a boundary that evolves alongside our knowledge. The philosophical implications of ultimate limits are equally profound. If the universe is infinite, then human existence is but a brief spark in an endless cosmic expanse. If it is finite, then every galaxy, star, and atom exists within a bounded framework, a contained story of matter and energy. Limits shape our perception of meaning, significance, and place within the cosmos. They remind us of both our fragility and our privilege, the ability to observe, to reason, and to explore a universe so vast that most of it remains beyond reach. Yet even as we confront the boundaries of space, time, and knowledge, the universe retains its mystery. For every horizon we approach, another emerges, just beyond observation or understanding. The cosmic event horizon recedes, the Planck scale beckons, and distant realms lie hidden in darkness. Limits, in the cosmic sense, are not barriers, but invitations, challenges to imagination, exploration, and contemplation. They frame the adventure of discovery, making every observation, calculation, and insight a step toward understanding the vast, intricate expanse of existence. Ultimately, the ultimate limits of the universe are as much about perspective as they are about physics. They define what is observable, measurable, and comprehensible, while simultaneously pointing beyond toward realms we may never fully grasp. They remind us that even in a universe as vast and seemingly infinite as ours, there is structure, law, and order, and yet profound mystery remains. Space stretches beyond sight, time flows inexorably forward, and matter and energy interact under rules that are both precise and elegant. Within these boundaries, the cosmos is alive with possibility, complexity, and wonder. As we close this journey through the universe, from the smallest subatomic particles to the largest cosmic structures, from the birth of stars to the fate of galaxies, we arrive at a profound realization. The universe's limits are simultaneously finite and infinite, knowable and mysterious, constrained by physics yet open to imagination. To ask, how big is our universe, is to ask more than a numerical question. It is to contemplate the nature of existence itself, the scales of space and time, and the boundaries of human understanding. We glimpse the infinite, yet we operate within the observable. We probe the beginning and the end, yet we remain humble participants in a story far greater than ourselves. The universe stretches outward in all directions, an ever-expanding tapestry of space, matter, energy, and time. Its limits, both observable and theoretical, challenge us to explore, to measure, and to imagine. And in contemplating these ultimate limits, we find both awe and inspiration. A reminder that the cosmos is vast beyond measure, mysterious beyond comprehension, and beautiful beyond words. In the end, the universe is more than its size. It is the totality of what can be known and observed, the mystery that lies beyond, and the infinite potential that stretches eternally outward. Its ultimate limits are not simply boundaries, they are the horizon of human curiosity, beckoning us to continue exploring, forever reaching toward the stars, toward understanding, toward the unknown.